Hello friends, so today we are going to discuss three questions, and these three questions will be from one question is from the projectile and other one is from your, you can say, force and equilibrium. Sorry about that. And in the first question, it is given that a projectile is launched from the ground at time t is equal to 0 with initial velocity v0 at an angle of theta of the horizontal. The acceleration due to gravity acting on the projectile is time dependent and increases linearly with time according to Gt is equal to alpha t, where alpha is the positive constant. Assuming motion takes place in a vertical plane and air resistance is negligible, obtain the expression for the horizontal range of the projectile and determine the value of the angle of projection theta for which the range is maximum. So this is, you can say, question that is related with the projectile, but the only difference is that the acceleration due to gravity is a time dependent function. Okay, so this is a major difference between the question, normal projectile question, and this one. Rest of the things are same. So let us draw the basic figure. So let us suppose this is a horizontal and the projectile is projected from point P, and let us suppose it takes the path something like this. Okay. And it is given that it is projected with initial velocity of v0 and at an angle of theta. And we assume that this above P is our origin, so we can say its coordinate is our 0, 0. And therefore we can find out its horizontal component as well as our vertical component of our initial velocity. So we can say that initial velocity component components and our x component will be equal to our v0 cos of theta, and y component is equal to our v0 sine of theta. Okay. So this we have taken as first derivative of our distance x, horizontal distance, and first derivative of y, that is our vertical distance. That is going to give us the velocities. And in this case, we have to remember that our acceleration due to gravity we already know more or less about this. So first point is that it will be always acting downward direction. So it will be always downward. And secondly, as per this question, increases linearly with time. Increases linearly with time. And linearly with time means we can write our g of t is equal to our alpha t. Therefore, we can write this acceleration in the vector form. So we can say acceleration vector, that is a vector, will be having over 0 comma minus alpha t. Okay. So which basically means that our horizontal acceleration, there is no horizontal acceleration, and the vertical acceleration is our time dependent. Okay. Now we can write the equation of the motion. Equation of motion, and for the equation of motion we can say that the double derivative of our x is going to give us acceleration in x direction, and double derivative of our vertical distance y is going to give us acceleration in the y direction. So let us consider our horizontal motion first. So we have our horizontal motion, and the gravity acts only vertically, therefore we can say that our horizontal acceleration is equal to 0, or we can say the double derivative is equal to 0. So if we integrate this once, okay, and this integrating, we are going to get our x single dot will be equal to a c1, that is our constant. And in order to find out our c1, that is our constant, we are going to make use of the initial condition. So we can say our initial condition, and that is the velocity at time t is equal to 0 is our v naught cos of theta. It means this will be equal to our nothing but our constant c1. Therefore we can write that our x single derivative, which is our velocity, is our v naught cos of theta. Okay. And similarly, or if we integrate it one more time, okay, so we can say second integration, and second integration will be giving us x of t is equal to our v naught cos of theta multiplied by t plus c2. And once again our initial condition, and here initial condition is this is x is nothing but our position. So we can say our initial position, and initial position we have assumed that it will be at the origin. Therefore we can say at time t is equal to this x naught is equal to 0. Therefore our c2 is also equal to 0. Therefore we can write that our position x of t, horizontal position, is our v naught cos of theta multiplied by t. And this is also true for our horizontal motion. Okay, so either way we get the same result, because this is our velocity in our x direction, that is horizontal direction multiplied by time t is going to give us the horizontal distance in time t. And similarly, we can write that our we can say similarly we can say that velocity in y direction will be equal to our v naught sine of theta minus alpha divided by 2, and this is our t square. Okay, it means this is our velocity at time t, initial velocity, and alpha is our this minus alpha by 2. Okay. And once again we can write that if we do its second integration, so second integration is going to give us as y of t is integration of our v naught sine theta dt minus integration of alpha by 2 t square dt. Therefore, we get that our y of t will be equal to our v naught sine theta t minus this comes as alpha upon 6 t cube, and let us assume that constant is our c3. And this y is our position vector, so we know that the position at time t is equal to our 0. So we get our c3 is equal to 0. Therefore, we get the equation for our position, vertical position at certain time t is equal to v naught sine theta t minus alpha by 6 and t cube. Okay. So in this case, we have used the basic method to find out the position vector, because the acceleration due to gravity is a time dependent function that is given as alpha t. So because of that, we have to solve it in this way. And let us find out the time of flight. And this time of flight is suppose represented by a capital T. Okay. And time of flight basically means that it starts from this point P and it is going to come back to the same horizontal position, that is our P prime. So under this condition, we know that our y of t will be equal to 0. Okay. And here the time of flight, we are going to put small t is equal to capital T. Therefore, we can write this y of our capital T is equal to 0. And we are going to use this equation. So we get this as our v naught sine theta capital T minus alpha by 6 t cube is equal to 0. And one of the t we can take as common. So we get this as our t, and we have our v naught sine theta minus alpha by 6 t square is equal to 0. So obviously this t cannot be equal to 0. So second function will be equal to 0. Therefore, we can write that our v naught sine of theta minus alpha by 6 t square is equal to 0. And from here, we can write our t will be equal to 6 v naught sine of theta and divided by alpha and its square root. So this is our time of flight. And now we are going to find out the horizontal range. and our horizontal range, suppose it is represented as our r, so obviously this will be nothing but a distance traveled in x direction at time t, capital T rather. Okay, and we already know that our x of t, so this will be equal to our v naught cos of theta multiplied by t, and we are going to substitute value of t. So we get that the range will be equal to our v naught cos of theta, and this comes as 6 v naught sine of theta alpha and its square root. So this is our range, and we have to find out the angle for maximum range. Okay, that is our final question that was asked. So we can say our angle for maximum range. Okay, and let me rearrange this range equation. We are going to take our, this can be written as 6 v naught cube upon alpha. This will be more or less constant, and we will left with our cos of theta square root of sine of theta. So it means our range is dependent upon this trigonometric function. Okay, so angle for maximum range, we can write that our r of theta will be our maximum, and this is possible that when this cos of theta and sine of theta will be also maximized. So we are going to maximize this function. So let us assume that our f of theta is equal to our cos of theta square root of sine of theta, and we can write this as square is equal to cos square theta and sine of theta. Okay, and let us assume a second function which is our g of theta, and that is equal to f square of theta. So we can write that our f square of theta is equal to our g of theta, and we have this as cos square theta and sine of theta. So we differentiate it, we get dg by d theta, and this will be our cos square theta multiplied by our we have to derivate it. Let me write it. So we get this as dg upon d theta, and cos will be giving me 2 cos of theta, and this will be minus, and here it will be sine of theta, and this will be a plus, and second cos, so this will go sine square, not correct, and then we are left with our cos square, that is sine, it will be coming as our cos cube theta. So we can take cos of theta as common, so we can say that our cos of theta, and we can write this as our cos square theta minus 2 sine square theta, and obviously we are going to put that is equal to 0, and cos of theta, either cos of theta will be equal to 0, so we can say our cos of theta will be equal to 0, or our cos square theta minus 2 sine square is equal to 0. Okay. And this cos of theta is equal to 0 basically tells us that theta is equal to pi by 2, or it is a vertical launch. Okay, and if they are vertical, the value of range will be equal to 0. Okay, so we are just going to ignore this part, and we are going to focus on the second equation. And from here we can write that our cos square theta is equal to 2 sine square theta, and we get this will be our tan square theta is equal to our 1 by 2, or our theta max will be equal to our tangent inverse of 1 by square root of 2, and this value is approximately equal to 35 degree. Okay, so this is a maximum value of our range, and here our this acceleration due to gravity is a time dependent, that's alpha t. Okay, so this is a first question. Now we come to a second question, and in this second question it states that an airplane moves with a constant speed v along a horizontal circular path of radius r. The pilot banks the airplane at an angle theta with the horizontal. Assuming that the only forces acting on the airplane are the weight and the lift forces, determine the banking angle theta required such that passenger experiences no lateral or sideways force. So here we have to remember one thing, that our this the lift force is basically always perpendicular to the wings. Okay, we have to remember this part. And so initially we can just draw the figure, and suppose this is a circular path and the position of the plane is somewhere here. Okay, and these are the wings, and it is r, and it is moving with the velocity v, and the lift will be also perpendicular, that is in the upward direction. Okay. And in the second part it states that, so this is our horizontal, and it banks the, and this is our plane, so this is our P. So plane, it is banking at an angle of theta with the horizontal. So our lift will be perpendicular to the wings. So this will be our lift L, and mg will be always in the downward direction. And we can just divide this into two components, and this angle will be also over theta. So we are going to get this L cos of theta, and this will be L sine of theta. So in this case we are given that it is moving with the velocity v, therefore we can write our centripetal acceleration centripetal acceleration A of c is equal to over v square upon r. Okay, and lift is always perpendicular to the wings. Okay, so we have to remember that. And so we divided our lift L two components, sine and cos. Therefore we can write that our vertical component is going to give us L cos of theta is equal to over mg, equation number 1. And then we can write our horizontal component which is going to provide a centripetal force. Therefore we can write our L sine of theta will be equal to m v square upon r, and this is equation number 2. Or simply we divide them and we write equation 2 divided by equation 1. So we get this as our L sine of theta, L cos of theta, and we have over m v square upon r, and we have our mg. M and m, L and L cancels out. So from here we get that our tangent of theta will be equal to v square rg, and our theta will be equal to tangent inverse of v square rg. So this is our angle, banking angle such that there is no lateral sideways force. Okay. Now we come to our third question, and third question, it states that a car moves on a uniform inclined planar surface that makes an angle theta with a horizontal. The driver attempts to negotiate a circular path of radius r on this surface with a constant speed. The coefficient of static friction between the tires and the surface is mu. Assume the car does not lose contact with the surface and air resistance is negligible. So based on this we have two questions. Determine the maximum permissible speed of the car such that no slipping occurs at any point along the circular path. And part B, determine the maximum permissible speed of car if the condition of no slipping is required only at the two side points of the circular path, that is point halfway between the highest and the lowest point on the incline. Basic figure is given to us. So we have a plane. This is a plane given to us, and the horizontal making an angle of theta, and the car is moving in a circular path. Okay. And these two are our side points. So this is the basic question. And in this particular question, we have to remember that the weight, that is our mg, will be acting always in the downward direction. We already know that concept. Okay. And other force, that will be normal, that will be always perpendicular to the plane. And the third force is our static friction, okay, and that is in the plane, and its direction we need to adjust as we are going to calculate. Okay. Therefore we can say that our forces acting on the plane not plane, and first one is our mg, and that will be acting vertically downward. And next is one normal n that will be acting perpendicular to the plane, and finally we are going to have our friction F, that is our in the plane, lying in the plane. So these are the three important forces that will be acting on this. So first of all, let us solve it for our vertical, the mg, and so let me redraw the figure. And in this case, we are going to draw our horizontal at a certain little bit of angular portion. Okay, so this is our horizontal. Okay. And on this, we can draw our this circular path on which it will be moving. And so for the sake of convenience, let us, because of mg we know it is always at downward direction, and suppose we can, this is our angle theta, and at any particular moment the car is somewhere here. Okay. So its mg will be in the downward direction, and we can divide this into two components. So this will be our angle theta, so we are going to mg cos of theta, and we are going to get this as mg sine of theta, and our normal n. Okay, so these are the forces for with respect to our mg as well as our n. Okay. Therefore we can write that our n is equal to mg cos of theta. So you can say our that our n is equal to our mg cos of theta, and based on this we can find out our friction. That is, the friction will be equal to mu times n, and we get this as mu mg cos of theta, and this value of friction will be our maximum value of our friction. And next is our, so these two forces is perpendicular, forces perpendicular to the plane. Normal as well as mg cos of theta are perpendicular to the plane. And next is our forces parallel to the plane. Forces parallel to the plane. And one of the force is down this, that is our mg sine of theta. Okay. And that is our mg sine of theta. And as the car is moving in a horizontal circle, there will be a requirement of our centripetal force. Therefore we can write that the car moves in a horizontal circle the centripetal force that is our Fc will be equal to mv square upon r. Okay. And we have to remember that this centripetal force will be always horizontal and it is always going to point towards the center of the circle. And this is when our circle is our horizontal. Okay, but in the given question, the circle is in the plane and that plane is at an angle of theta. Okay, so circle is nothing but not actually horizontal, but it's making angle of theta with the horizontal. So we have to remember this. Therefore, from here we can write two important things, that Fc is always horizontal and second part, this our centripetal always points toward the center of the circle. So you can say points toward center of the circle. So in this case, we have to remember that all this discussion is being carried out with respect to when the circle is our horizontal. But the given circle is making an angle of theta with the horizontal. Okay, so we have taken this is our horizontal path. Okay, just to differentiate it. And so we know that now we come to the given problem and we are going to solve it for our this centripetal force. Okay. So we know that our plane in which we are having a circular path is inclined at angle theta. Okay. So it means, let me draw. Okay, and for this we can say that if our circle is our horizontal, then in that particular case our centripetal force will be always acting toward the center. But this circle is at an angle of this we have taken as horizontal. Okay. Sorry, one second. Yeah. So this is the one corner of the plane in which the circle is there, and the horizontal we have taken something like this, and this is angle theta. So now our centripetal force will be also, you can say, will be always parallel to the horizontal axis. So this is our horizontal axis. So the centripetal force will be also parallel to this. So this is our centripetal force. And now we can divide the centripetal force into two components. And these two components are going to give us the so one will be our perpendicular and now this will be our parallel component. Okay. So these are the two components of our centripetal force. Okay. Therefore, you can say that so we said that the plane is inclined at a angle theta. So we can say that our centripetal force has two components. Okay, so let me redraw this figure, and so we are having a plane. So this is our plane, and this is a horizontal and making angle of theta, and we are having a circular path, and for any position we know that our this centripetal force will be acting, that is parallel to our horizontal. Okay, so our centripetal force will be acting something like this, and it can be divided into two components. So one component will be parallel to the plane and other one will be toward the center. So we get this as our FC parallel and this is our FC perpendicular. Okay. And therefore the FC is having two components. First component is our parallel to the plane, which we call as our FC parallel, and that is equal to FC cos of theta. And we are going to have a second component that is our perpendicular to the plane, that is a FC perpendicular, which will be our FC sine of theta. Okay, so this is the important part here, that the centripetal force is going to have our two components. Okay, and therefore the parallel component, that is FC parallel, is going to fulfill our centripetal force requirement. Therefore we can say that our centripetal force requirement, and that will be fulfilled by our parallel component, and its value will be equal to our mv square upon r, and this comes as our cos of theta. And now we come to our part A. And part A, it suggests that we have to find out a point, okay, critical point rather, and for that critical point we are going to prove that for no slipping is going to take place at that critical point. If at that particular point there is no slipping, entire circle there will be no slipping. Okay, so we can say part A states that no slipping anywhere when the car moves around the circle. And so for this we are going to identify the critical point. Identify the critical point. And the critical point, or we can say the worst case point. Worst case point. Now this worst case point is nothing but a point where the force of friction will be stretched to its maximum limit. Okay. And this point, the critical point, will be the lowest point on the incline. This will be our lowest point on the incline. And we already know the forces that will be acting on the particular point. Okay. So the lowest point will be somewhere here. So this is our lowest point. So we can just once more draw here. So this lowest point will be somewhere here. Okay. And we know that our mg will be downward direction, and its component is our mg sine theta as well as our mg cos theta. Therefore, we can say that so the lowest point are inclined, and we know that this gravity, or we can say the component of gravity, component of weight pulls down the slope, and secondly, the centripetal force also lies down the slope. Centripetal force also lies down the slope, and a centripetal force means a component of it. And we just said that the centripetal component will be always our this parallel component acting toward the center, and therefore we have our this component weight that will be down the slope. This component we know is our mg sine of theta, and the centripetal force component is our fc parallel, and that is our mv square upon r cos of theta. So these both components are in same direction, and it will be balanced by our total friction. Okay. So we can say that the friction must balance. Let us call this as equation number 1 and equation number 2. The friction must balance our first equation plus the second equation, and therefore we can say that the required value of friction will be equal to our mg sine of theta plus mv square upon r, and we have our cos of theta. So this is the required value of friction. But we know that for no slipping condition, this required value should be always less than equal to the maximum value of the friction. We can say that no slip condition the required value of friction is less than equal to our maximum value of our friction. So we simply required value is our mg sine theta plus mv square upon r cos of theta. Maximum value is our mu mg cos of theta, and from here this m simply goes away, and we can just sort it out for our velocity. So we can say that v square upon r cos of theta less than equal to g we can take as common, so this will be coming as our mu cos of theta minus sine of theta. And from here we can write that our velocity will be equal to, let me put it less than first of all, so this will be less than equal to, this will be becoming rg mu cos of theta minus sine of theta and its square root. And the maximum value without slipping, V max will be equal to our gr mu cos of theta minus sine of theta and its square root. So this is our maximum value of friction without slipping at its critical point, and this value is our, you can say, true for entire circle, because the maximum value that the friction is going to required, that is going to face, is at the lowest point. Okay, rest of the value of the friction will be always less than the required value. Okay, and we come to our part B, and part B, it says about the side points. So part B, no slipping only at the side points. No slipping at the side points. And the side points are mentioned in the figure. So let me draw it here. And please remember, the plane, horizontal plane, we have taken at a certain angle. So this is the horizontal plane, okay, and make an angle of theta. And the side points is given at, this is one of the side point and this is other side point, moving this direction. Okay. So we have take any of one of the side point and try to find out. Okay. And now, so if the circle was horizontal, we know that the centripetal force will be acting toward the center. Okay, but it is at an angle, therefore the centripetal force will be having two components, and toward the center it will be our parallel component, okay, and our perpendicular component will be of our, this we have already discussed it, yeah, this part. Okay, because we know that our centripetal force is bound to be horizontal, so there are going to two components, one toward the center and other one in the perpendicular direction. Okay, and this will be universally true for entire this. Okay. And here we have to remember one thing, that for this particular point, okay, so let me assume that the side point is exactly at this point. Therefore, our mg will be acting in downward direction, and we can divide this mg, this is our angle theta, we get mg cos of theta, and we get our mg sine of theta. Okay. And our circle point is somewhere here. So from here we can clearly see that our gravity, or that is a weight mg, does not having any component that is toward our center of our this circle. Okay, neither in the same direction, radial, or now in the opposite direction. Okay, so the only component that is going to provide our centripetal acceleration will be the frictional part. Okay, therefore we can say for part B, there will be no role of this mg. Only part will be our FC parallel. Okay. So we can say at side points, we know that centripetal force points across the slope. Centripetal force points across the slope. And secondly, it also the gravity acts along the direction of motion. Gravity means our weight mg. Weight acts along the direction of motion. Direction of motion. Okay. Therefore, we can say that our weight does not affect the centripetal requirement. Does not affect the centripetal requirement. Centripetal requirement. And the friction must provide the in-plane centripetal force. In-plane centripetal force. Or we can simply say that our this friction will be only responsible or balancing our this FC parallel. Therefore, we can write that our centripetal, that's our FC parallel, mv square upon r cos of theta, should be less than equal to mu mg cos of theta. Okay. And here we can also write this as F requirement will be equal to our, only because of our FC parallel there is no weight component, and this will be equal to our mv square upon r cos of theta, whereas in the lowest point the friction required will be dependent upon the weight component as well as our this centripetal our what it is, one second, centripetal force FC component. Okay. But at the lowest point this weight component is equal to 0. Okay. That is not in the direction of our center away or along the radial direction. So therefore our F requirement for no slipping should be always equal, less than equal to our F maximum friction. So based on this we can easily write it. Okay. And we can sort it out further, and this cos and mass goes away. Therefore we get that v square r is less than equal to our mu g, or we can say that our velocity v is equal to mu g r and its square root, and this velocity is our maximum velocity at the sideway points. Okay. So this was our 3 questions. Okay. First question was from the projectile and in that projectile we discussed that our acceleration due to gravity was a time dependent function. Okay, and other two questions were a basic of our equilibrium of forces, okay, or we can say static equilibrium. So this completes all the three questions. Thank you.